In this session, we are going to talk about data storage in memory, right? So here I will mostly be focusing on this integer data type. But let's talk about the data storage first of all, that how data is stored. Now, if I talk about computer's memory and the data representation in computer system, so we know that the computer's memory consists of millions and billions of transistors, right? And at any time, a transistor can be in one of the two physical states labeled as zeros or ones. And each transistor, this is a very important point, that each transistor carries one bit of information. So when we combine this 8 bits together, it is termed as 1 byte. And when 2 power 10 bytes are clubbed together, that is 1 kilobyte. 2 power 20 bytes is termed as 1 megabyte. 2 power 30 bytes together is 1 gigabyte. And 2 power 40 is 1 terabyte. Now, how this logic 1 or logic 0 is depicted? So transistor uses something called the voltage levels as the binary values. So transistors operate in high and low voltage levels. So voltage range dictates the binary value on the wire, right? So if I talk about logic 1, when I'm talking about 1 bit, it means internally the transistor has detected a range of 2.8 volt to 3.3 volt. That means whenever the voltage range is between this range, that is 3.3 to 2.8. So this is depicted as logic 1 in the diagram you can observe here, right? Similarly, if I talk about logic 0 or the 0 bit, that means the transistor goes through this low voltage range, that is 0.05 volt to 0.0 volt. And between this range, if you observe, between this range, if any signal is there within this voltage range, this is simply discarded, right? So that's the idea of logic 1 and logic 0. So I hope this is clear. Now, if I talk about bits and bytes, so as we already observed this fact that transistors can have two distinct states, so computers uses bits, right? So bit is the short form of binary digit. So generally, the low voltage is associated with logic 0 and the high voltage is associated with logic 1. Now, since the single bit offers limited range, so it is grouped in bytes. So collection of 8 bits together is termed as 1 byte, and remaining terms we have discussed already in this part, right? Now, a single datum can use multiple bytes definitely. So if I talk about n bits, if n bits are given to us, then we can represent 2 power n distinct values. We'll be talking about this one. Now, integers, if I talk about specifically about integers, so integers are of two types. One is signed integer and the other is unsigned integer. So signed integer is the one, it is basically, if I say, in the domain of mathematics, that is the set of integers. So it contains negative numbers, positive or zero. So such kind of integers are termed as signed integer. Now one question comes in mind that for positive number and zero, we can convert them into direct binary. What about negative numbers? How negative integers are stored in memory? So for that, we use a system called 2's complement system. Today, most of the computing systems uses 2's complement number system in order to represent positive, negative or zero, these integers, right? So in this, the positive number is represented as it is. That means you take the number and convert into binary, and the negative integer is converted into 2's complement form, right? We'll be talking about this one. Now these are some of the examples, right, of 2's complement number system. So here some of the examples are shown in 16-bit using 2's complement system, and this is the range of the range of a number system in case of 2's complement system. So if you are given k bit number, so in that case the smallest number you can represent is minus 2 to the power k minus 1, and the largest integer that you can represent is positive of 2 power k minus 1 and then again minus 1. So that's the idea. I'll show you some examples, through that you will be getting the clarity. Now, if I talk about unsigned integer, in unsigned integer, so if I talk about n bit unsigned integer, it can represent 2 power n distinct values, and these are the various combinations that you can observe here, right? So if you have 3 bits, if you have 3 bits, you can clearly observe the smallest integer that you can represent is 0 and the largest one is 7, that is 2 power 3 minus 1. So if you are having n bit number, so in case of unsigned number, the minimum value that you can represent is 0 and the largest value that you can represent is 2 power n minus 1. So that's the idea, and these are the various representation of integers in various forms. So this is the decimal representation of 123, This is the octal representation, right, of this number, that is 123 in octal is 0173 in base 8. Similarly, 123 in decimal is converted as hexadecimal here. So this is 0x7b. So 0x is the prefix used to represent hexadecimal numbers. And in order to represent long literal, we use the suffix l, right? For short, we do not have anything. So these are some of the examples of integer type, long type, and short type. So enough of this. Now what I will do, I will use the char data type in order to explain the storage of these numbers. So I'll be taking an example for positive, 0, and negative, so that you get a clarity on this one. So I'll go to this my editor, and here I will write char, let's say variable name a, and I'll store, let's say, 17 over here. So in memory, how this is laid out in memory, I'll be talking about this part. Now if I print the value of this, let's say using percentage %c, so this will print the character. So instead of this, I'll be printing first of all for 65. So for 65, if I compile this, let's say hello.c, and then in output I'll name it as hello, and if I execute this, this will print a. And the very same thing, if I print it using the format specifier percentage %d, so this is going to print the number corresponding to it. So I'll compile and execute together. Okay, so dot slash hello, hit enter, and we are having the number. So to keep it simple for now, I'll use 17 here just to show the binary representation easily, right? So now I'll perform analysis on this one and show you that how this positive number is actually stored in memory, right? So here, if you observe, this is 17. Now the question is that how this 17 is stored in memory. So this occupies 1 byte. So 1 byte means we have 8 bits. So if I represent this 17 in 8 bits, so 17 would be, so this is, I'll convert into binary this one. So this is my 12, and this part is 15, right? So binary of 17, if you just divide by 2, this number, if you keep dividing by 2, you can convert by the traditional procedure. So here I'll be writing the binary of 17, that is, this part is 1, and then next 3, and then here we are having 7, and then 15. So 15, after 15 I need 17, right? So this part is 17. So 8 twos are 1. So if I can represent 8, so this one is 8 actually, and then this part will be, this is representing 17, right? So this one is 2 power 0, and then 2 power, this has the weightage 2 power 1, then this has the weightage of 2 power 2, and 2 power 3, and then 2 power 4. So 16 plus 1, that is 17. So how many bits I've used here? 1, 2, 3, 4, 5. 5 bits. The remaining 3 bits I'll plug it as 0, 1, 2, 3. So in my 1 bit of storage, sorry, 8 byte, that is 1 byte of storage, in my 8 byte of storage. So let us say if this is the address, let's say 200, and this is my variable a, so my 17 in memory is stored in this way, right? So this is the memory representation of 17 here. So that's the idea. Now, so this MSB, if you observe, the most significant bit, this represents the sign actually. So this is positive 17. Now what about if I write, let's say, negative 17? What about this? How this is stored in memory, right? So we want to know about this part. So if you observe now, so now I'll be analyzing this negative 17. So this is stored using 2's complement form. Now 17's binary is something that we know. Now to convert a number into 2's complement form, that is negative 17. So what I will be doing? So just write all the bits. So start writing the bits from the rightmost side, right? Start copying the bits as it is. The moment first one appears, just you flip remaining bits. I mean to say, start from the rightmost. So if you observe here, if I arrive at this, I can write 1 over here. After this, whatever bits are there, flip the zeros to 1 and ones to zeros. So here what I will do, wherever zeros are there, like 3 zeros, I'll write 1 1 1, and this one I'll flip it to 0, and this one I'll flip them to 1 1 1. If you have doubt on this one, I'll take one more example. For example, you have a number like this. Let's say 1011101000. Now you have to convert this number, and let me write 0 over here. So you have to convert this number into 2's complement form. So very simple. What you can do, start from the rightmost side and copy the bits as it is. So 1, 2, 3, 4, copy this till you encounter the first one. You write this first one as it is. So I'm repeating again, copy this, copy the bits from the rightmost side. So 0, 0, 0, all of this you copy as it is till you get the first bit as 1. The moment you encountered this first bit as 1, that means till this much part it will be same. After this, whatever bits are there, just flip all of this. So I'll copy and paste. So this 0, I'll make it 1, and this 1 1, I'll make it 0 0. This 0, I'll convert to 1. 1 is there, flip it to 0 0 0, flip it to 1. Flip this to 1. So this is the 2's complement of this given number. So there is a method for this one. You can take this number, convert into 1's complement form, and then add 1 to that. So that's a traditional way. But again, just to show you that how to convert it quickly, I have just considered this approach. So in memory, let us say if variable a has the address, let's say 200 itself, and the memory of 1 byte will appear like this. So this is the memory storage for 2's complement number, right? So now this is the idea. So let me just show you that if this is the number given to you, how will you decode that, whether it is negative 17 or which number it is? So first of all, observe the most significant bit. Observe this one. So if the MSB is 1, that means the number is negative. So it means the integer is negative. This is negative integer. So by observing the MSB, I understood this. Now what I will do to get the value of the number. Now because of this MSB 1, I understood the number is negative. Now I need to get the value of this number, right? So I'll take this number as it is along with the MSB, and again I'll decode this one. So in order to decode this one, I have to convert from 2's complement form to normal form. So again apply 2's complement procedure. That means start from the rightmost side and copy all the bits as it is till you get the first one. So here I got first one in the very first step. So I got first one as it is. Now these remaining bits, leaving the last bit as 1, I will flip the ones to zeros and zeros to 1. So let me just copy this, and here 3 ones are there, I'll write 3 times 0. Here 0 will flip to 1, and here this will flip to zeros. And if you observe, this is nothing but this is 17 in base 10. This is 17 in base 10. So what did we understand? In order to store negative number, or to represent negative number, you take the magnitude of the number and you convert it into binary. Once you have the binary, so this represents, if you observe here, right, that at this point, if you observe, this is the binary of positive 17. Now this one you have to represent in negative. So negative integers are stored using 2's complement form. So you take this number and convert into 2's complement form. That means you start from the rightmost bit and copy the bits as it is till you encounter the first one. So in the very first place itself, I encountered first one. After that, flip all the bits, and this is the 2's complement representation of this minus 17, and this is how it is stored in memory in 8 bits. Now in order to decode the number, just write the number as it is and again apply the reverse procedure. That means on the given number, by observing the MSB, we'll understand it is negative number, and again apply 2's complement form to get the value. So this is how your negative number is stored. And for 0, so let's say if I'm writing here, let's say as 0, so for minus 17, if I just show you, so if I compile and execute, so you can observe minus 17. This very same number, if I print it using the unsigned form, compile and execute, so you can observe this is a large integer coming, because there are a lot of bits that have converted to ones. That's why when I print it using percentage %u, I have a very large integer in front of me, right? So that's the idea. So for 0, if you have to store 0, then write all the bits as 0. So let's say if you have to store 0 in 1 byte, then all the bits will be written to 0. Here all the bits will be written to 0. So 1, 2, 3, 4, 5, 6, 7, 8. So that's the idea. So now if I talk about this 8-bit data, 8 bits. So just now we have talked about the range, that is if I have k bits, right? So instead of this, so in if I talk about k bits signed integer range. So the minimum value that I can represent is, the minimum value will be minus 2 to the power minus, so minimum value will be minus 2 to the power k minus 1, k minus 1, right? And the maximum value will that can be represented in this range is, that will be positive of 2 to the power k minus 1 and then minus 1. So in 8 bits, if I talk about 8 bits, so the max and min, if I compute the max and min in this case, so this will be minus 2 to the power k minus 8 minus 1, that is 7. And the largest integer that I can represent in 8 bits is 2 to the power 7 minus 1. Now this is equal to minus 128 and this will be equal to 127. So that's the range actually for 8 bits. Similarly, if you are having any number of bits, you can represent this range. So in simple terms, if I talk about this in simple terms, if you take, let's say, 3 bits range and just write down all the numbers that is from positive to that is from positive to binary and negative to binary, if you convert, then you can get to see the range clearly. So this is how you compute the range, right? So that's the idea. If you want to know how it works, why it works, definitely I'll record something regarding number system in extensive detail so that you get the clarity. In this session, my only agenda, my clear objective was to explain that how positive integers are represented in memory, how negative integers are stored in memory, and how 0 is stored in memory. And most importantly, if k bits are given to you for signed integer, then how can you compute the range of that? Similarly, if you have 32-bit integer, so instead of k, just replace 32. If you have 64-bit integer, instead of k, you represent 64 bits, right? So that's the idea of data representation with regard to integers. So I hope the session was useful and you understood the data storage with regard to integer, both signed and unsigned. So for unsigned, you can just write this unsigned keyword here, right? So here you can represent unsigned numbers. So you can write 18. So here zeros, so this unsigned modifier is used for representing zeros and positive numbers. So now if I write, let's say, 67, so around 67 whatever numbers are there, so 67 is printed here. So the ASCII value for this one is C, the character, right? And then the numbers are printed. So you can observe here that unsigned percentage U, it prints 67, and for percentage D as well. But if I write, let's say, negative number, if I write negative 17, let's say, and compile and execute, so you can observe here that even for percentage D, it does not prints negative. That means this minus 17, if you observe, negative 17, so negative 17 is this. So in case of unsigned, this MSB, this most significant bit, is not considered, this is not considered for 2's complement. So what it does, it takes this number as it is and converts directly. So if you convert directly into binary of this one, so if you just search out, if you convert this into binary, this will be 2, whatever that number was shown, that is 239. So in this case, in case of unsigned, so let me just write it. In case of unsigned integer, even you are writing this, let's say, negative 17, so negative 17 is stored in memory in this way, and when it is being read in unsigned form, then the value is coming 239. So that's a very important observation for us. So in unsigned, that's why the range is from 0 is the least smallest integer, and 2 power k minus 1 is the largest integer. So that's the idea. So I hope the storage of signed integer and unsigned integer is clear.